everybody. My name is Christian Mackey. This is my Physics 114 video project. I attend North Seattle College, and this is currently fall quarter 2024. My instructor for this class is the one and only Dr. Azita Fade. And let's get to the research question. All right, so this is the research question. In the Soapbox Derby, young participants build non-motorized cars with very low friction wheels. Cars race by rolling down a hill. The track at Arkins Derby Downs, where the national championship is held, begins with a 55-foot-long section tilted at 13 degrees below horizontal. The questions at hand are, what is the maximum possible acceleration of a car moving down the stretch of a track? And if a car starts from rest and undergoes this acceleration for the full 55 feet, what is the final speed in meters per second? The change values in this equation, or just this whole thing, is that the 55-foot-long section will now be 3.3 feet, simply just because I could not recreate that at home of a 55-foot-long ramp. But anyways, our known values in this is that our angle of inclination is at 13 degrees. Our length of incline section is 3.3 feet. Our initial velocity is at 0 meters per second from right here if a car starts from rest. Our gravity in this is 9.8 meters per second squared, like how it always is on Earth. Our initial position is 0 feet, and our final position is 3.3 feet. My hypothesis is that I hypothesize that in this equation, the final speed and max acceleration will be very similar to one another, and that due to them both playing a significant role in each other, we will need the maximum acceleration to find the final speed. My materials to understand this and create my ramp is that I need a toy car, a protractor, boxes, a ramp made from cardboard, measuring tape, which I will just be calling ruler, and this is the final result. So right here is that we can first see that this is at a 13-degree angle, and creating the ramp is just using some boxes, and here's the toy car, and this is the ruler at hand. In the end, it looks like this: 3.3 feet long, 13-degree angle, and there's our toy car. So after recording this, I put this up right on Logger Pro, and the first thing I had to do was go to the scale section. I had to make sure that just Logger Pro knew that this length is 3.3 feet, and right after that, I decided to put the axis on right here on the car just to gain a further understanding of what's going on. Next, I'm going to click on every time the car moves each frame, and that's through this 3-dotted button right here. And through that, I get this. Pretty simple, pretty fun. And with this, it just basically helps create some graphs that gain a further understanding of what's at hand. So this creates my XY graph and my X velocity and Y velocity graph. With this, we can see that there's a linear increase and a linear decrease in our X and Y graphs. And when looking at our X velocity and Y velocity, we can see that there's an exponential increase and an exponential decrease with the best fit line. Now, this doesn't really come in hand for the equation and anything really, but it just kind of gains a further understanding on what's at hand, and it's always just fun to do. Time for problem solving. So we know our known value, and these are theta, which is 13 degrees, final length of incline, which will just be xf, which is 3.3 feet, our initial velocity, which is vi, 0 meters per second, our gravity, which just will be g, 9.8 meters per second squared, our initial length of incline, xi, is 0 feet. With doing this, it's time to solve the first question, which is the maximum possible acceleration. To find this, the equation at hand is A equals G sine theta. With our known values, we are able to fill in some blanks here. We know that G is 9.8 meters per second squared. Theta is 13 degrees. So when putting this in the equation, we get A equals 9.8 meters per second squared sine 13 degrees. And after calculating that, we'll get A equals 2.2 meters per second squared. Here's a little drawing to just gain a little bit more knowledge on just our understanding on just the question. To find the final speed, this is a little bit more tricky. We're going to have to use a kinematic equation, which is final velocity squared equals initial velocity plus 2 times acceleration times delta x. And delta x is just the change in the length here, which we get from xf minus xi, which is just the final length subtracted by the initial length, which is just 3.3 feet subtracted by 0 feet, which gets us our delta x, which is just 3.3 feet. So in order to solve this, we're going to have to change delta x from feet to meters. So to do this, we got to multiply 3.3 feet by 0.3048 meters over 1 foot. This then gets us 1.00584 meters. With this, we're able to finally solve what our final speed is by plugging in everything. First, understanding that the initial velocity is 0, so we can simply just scrap that. And we know that our delta x is, 1.00584 meters, but we won't plug that in just yet. First, we see that there's squares, so we're going to have to square root. So after square rooting final velocity squared and 2a delta x, we get VF equals root 2.2 meters per second squared, which is our a value right here, times 1.00584 meters, which is from right here, our delta x. This then gets us VF equals root 4.42569, which, after just putting this in a calculator, gets us our final speed of VF equals 2.104 meters per second. And here's just a little line just to show that this is 3.3 feet. But yeah. In my conclusion, my hypothesis turned out to be correct. Both max acceleration and final speed had very close answers. My maximum acceleration turned out to be 2.2 meters per second squared, and my final speed turned out to be 2.104 meters per second, which is relatively close. I was also correct in expecting the maximum acceleration to play a critical role in calculating the final speed, since the maximum acceleration, known as A, was in the kinematic equation used to solve the final speed. Final velocity squared equals initial velocity plus 2a times delta x. Thank you so much for watching this. I had an amazing time doing this, and yeah, hope this helps anybody. Thank you.